Okay, we'll get started. I finished grading your midterm exams and I posted grades online. And if you have any questions, you can come by office hours to take a look at your exam. I don't post solutions, I don't return the exams, but if you want to see your exam, just come by one of my in-person office hours to take a look. So I have office hours today at I guess 11:30. You can come by then. The median was 89, so we're just going to leave the grades, no adjustments or anything like that. I think overall, well, I mean, with a median of 89, I think that's pretty good. So, okay. Let's take a look at today's lecture content. Okay. So we started on Monday talking about maximum likelihood estimation, and we left off. This is kind of where we said for linear regression, what we want to do is we want to maximize this likelihood function. So the likelihood function is a function of the weight vector W. All right, we treat all of the observed data, your actual values t, the target values, the input values x, and the variance as fixed values, and we said what is the values of W that maximize this likelihood? And so we said, well, if we treat every observation as independent, we can just say it's the product of all of these probabilities. And if we assume that the observations have normally distributed noise, we said the predicted values, kind of the true relationship, falls along this linear relationship, W transpose X, and then there's some random noise, sigma squared, that determines kind of where the actual observed value is, right? And so if we said, well, if this thing comes from a normal distribution, if the random noise is can be modeled with a Gaussian distribution, then the total likelihood is going to be the product of all of these Gaussian densities. And when you want to maximize a product of a whole bunch of Gaussian densities, it turns out that it becomes equivalent to minimizing the sum of squared errors because of the way the Gaussian density is written out. So if you look at the product of the log likelihood of the likelihoods, and we want to maximize the likelihood function, this is equivalent to maximizing the log likelihood function. And when you try to maximize the log likelihood function, as you pick it apart, these things end up being constants. The sum of these things end up being constants. And we have a negative value here multiplied by the sum of this, and this ends up looking like the sum of squared errors. It's the difference between the actual value t sub n and kind of the predicted value, or in this case, what we presume to be the true relationship, this linear relationship between the target values and x, W transpose x. And so we're effectively trying to minimize this because it's being multiplied by a negative value. So that's so maximizing the likelihood function ends up being equivalent to minimizing the sum of squared errors, and therefore we end up with the same solution. That is the value of W that maximizes the log likelihood is x transpose x inverse x transpose t. And I think this is where we got to at the end of Monday's lecture. And we said, well, you know what? One thing we noticed is that there's no sigma squared. What if we wanted to maximize the sigma squared, that we maximize the likelihood of the data, with respect to sigma squared? What value of sigma squared would maximize the likelihood of the data? So if this is the likelihood, and we're going to treat everything else as kind of fixed, then what value can we use to maximize this likelihood? What value of sigma squared should we plug in? So that's what we'll take a look at on this slide. So on this slide, we're going to pick up same spot, this line right here. Here's the likelihood, here's the log likelihood. And what we're going to do is we're going to just plug in our current estimates of W. So we're going to just put in W hat into our log likelihood function. We're going to say, can we maximize this log likelihood function? Can we figure out the value of sigma or sigma squared or whatever that's going to maximize this log likelihood function? So what do? We're going to take the derivative of the log likelihood with respect to sigma. We'll set it equal to 0. We'll solve for sigma and see what we get. All right, so the derivative of this with respect to sigma, there's no sigma here, it's a constant, so that zeroes out. Negative n times log sigma becomes, the derivative of that is n over sigma. Here I've got 1 over 2 sigma squared times this thing. This whole thing is a constant with respect to sigma, so that's fine. And so basically I have negative 1 sigma to the negative 2, or I'm sorry, negative 1/2 times sigma to the negative 2. And so when I bring that down, it becomes sigma to the negative 3. Okay, positive. So I have this. And so I'm going to set this whole thing equal to 0. We're going to solve for sigma. So I bring n over sigma, negative n over sigma to this side. I'm going to multiply both sides by sigma cubed. And I'm going to divide both sides by n. And this is what we end up getting. We end up getting the value of sigma, or sigma squared, that solves this equation, that is where the derivative of the log likelihood is equal to 0. The value of this is when sigma squared is equal to 1 over n times the sum of t over n minus w transpose xn squared. And so this thing is equal to the mean squared error, right? So we're taking the sum of squared errors and we're dividing by n, and we have the mean squared error. How is this different from the variance? So if you have a sample of data and you ask, what's the variance between this and, well, I guess if you just have the mean. The difference is we're dividing by 1 over n rather than n minus 1, okay? So to maximize the likelihood, the value that's going to maximize the likelihood, and this is true for kind of any, just if you take a random sample and you say, I want to figure out the variance, estimate of the variance that will maximize the likelihood of my data, it's going to be 1 over n. But then if you want to get a value that is unbiased towards the kind of population parameter for variance, it's going to be 1 over n minus 1, right? Okay, so anyway, this is what we have. The value, the maximum likelihood estimate of our variance turns out to be the mean squared error of the model. Okay, so this is, that's what we have. And so if we plug this back in, and we say, okay, well, what is the log likelihood if I plug this into, to see what is the log likelihood at the maximum. Okay, so we'll just replace sigma with sigma hat basically. Okay, and if I have sigma, I could do sigma hat squared over 2. And this is basically what we have. So I'm just replacing this, and then replacing sigma squared with sigma hat squared. Okay, and if we take a look at this, right? So with the definition of sigma hat squared being 1 over n times this, okay, I can kind of plug that in, right? So I'm going to get, so if I multiply sigma hat squared by n sigma hat squared ends up being this portion, right? So if I multiply sigma hat squared times n, I'm going to get this, and so I'm replacing this thing with n sigma hat squared. Okay, and so if I do that, well, these things cancel out, and I get negative n over 2. And that comes over here, so I get negative n over 2, 1 plus log 2 pi, so just some constant over here multiplied by how many observations we have, minus n over 2 log sigma hat squared, okay, or sigma squared hat, whatever, okay, our estimate of the variance. So this is what we have. This is the log likelihood, the value of the log likelihood here. And so what we notice is that there is a negative value here. Okay, and so that means if we decrease sigma squared hat, or the estimate of the variance, if this decreases, then the log likelihood of our data increases. Okay, so what is sigma squared? Sigma squared is the variance of the error that we have in the model. Okay, and in our case, the error is kind of the leftover variation after our model makes a prediction, right? So if we have, we're basically taking the actual values minus the predicted values. Okay, actual values minus the predicted values, because if we look at what this is, actual values minus the predicted values. And so if we can tune our predictions so that they're closer to the actual values, this whole thing is going to shrink. Right? This whole thing is going to shrink if we can get our actual values closer to the predicted values. Right? I mean, the predicted values closer to the actual values. And so it's basically what we kind of have left over. It's basically the mean squared error after we make a prediction. And so one way we can kind of decrease the amount of error is to make the prediction function as complicated as possible so that the remaining, I don't know what just happened, the remaining error is as small as possible, right? So we can just kind of keep adjusting whatever this is, keep adding terms or something so that our predicted values get closer and closer and closer to the actual values, and we have just a tiny bit of kind of leftover error, all right? And this will effectively maximize the likelihood or maximize the log likelihood of our data, right? That we have. But on the other hand, we also know that having a highly complicated model is not going to be the best. This is going to put us at risk of overfitting our data, and so perhaps we don't want to just keep doing that. But if you want to maximize, quote unquote, the likelihood of your data, you can say, this is, this is the true model. If the true model is whatever you have, then and the actual values are very close to what you are saying the true model to be, then that means you've got, that maximizes the likelihood. But chances are what you are claiming is the true model is not quite right either. Okay. I'll try to think of an analogy here in a moment. Let me give you your first view quiz answer for today, which is the letter B. B as in bear is your first view quiz answer for today. So remember, the likelihood of your data is kind of a measure of, what's the probability of getting these observations if the true model follows some form, okay? And so there's always some random noise here. And if you can say basically your observations match the, whatever you're saying the model to be, then that's going to increase the likelihood of your data, okay? But there's always kind of this question of how right is the actual model, the model that you're claiming, right? And so we can continue to increase the likelihood of our data by making our model more complicated, and that's going to increase the likelihood of our data according to the model. But now we run the risk that our model itself is wrong, okay? And so it's good to kind of talk about this concept of information, which is basically how much information do we have about some unknown parameters based on the data that we have, okay? And so we'll get into this concept of Fisher information, which I think gets mentioned in some of your other classes. And, a lot of these concepts gets mentioned several times in different classes across different places. And so hopefully by, hearing different people talk about the same things, it helps you build up a fuller picture of things, right? Everybody kind of emphasizes what they think is kind of the important aspects of this. So before we get into what Fisher information is, I want to just talk about derivatives, okay? And so let's just think about simple univariate functions. So one variable in, one variable out, or one value in, one value out, okay? And the derivative tells you about the rate of change. Yeah, so it's basically the slope. You'd have the slope of the tangent line. And so if the function is changing values rapidly, your slope is high, you have a big derivative. And if the function is flat or changing values, the rate of change is low, your derivative is quite small. The second derivative tells you how quickly the slope changes. Okay, so it tells you about the curvature. So if you have a very big second derivative, that means the slope changes rapidly. You've got kind of a sharp bend in the curve. So you're going from maybe very sharp slope upwards to a very sharp slope downwards. There's a rapid change in the slope. Okay, whereas a small second derivative indicates that your slope is changing gradually. Okay, so it's a kind of a smoother, less curvature, right? The sign of that second derivative tells you whether the slope is the concavity, right? Whether you're kind of concave down or concave up. So positive second derivative means you are concave up. You're going from basically negative slope to positive slope. So that's going to kind of form a bowl, a concave up. Whereas a negative second derivative would indicate you have concave down, and if you have if the derivative is equal to 0 at some point x is going to be a local max. And on the other hand, if the second derivative is 0, then you don't know the concavity of the function, and it could be something like an inflection point or something like that. There's stuff that could be going on, right? So this is kind of your review, I think, from what, 31A or something, so way back then. And then we can kind of generalize this to talk about gradients, okay? And so the first derivative has a multivariate. The gradient is kind of like the multivariate generalization of the first derivative. So you have some function where it takes multiple inputs, n real value inputs, and the function maps those values to just one real value output, right? So simple example is you've got two inputs, you have an x and a y coming in, and it produces one value out, a z, or something like that. And, we can visualize that as a surface, and anything higher than that gets harder to visualize, but it's kind of the idea that you got multiple ins, you get one out. So let's assume we have some n-dimensional vector w, okay, and we have a function of w. So then we say, well, what is the gradient of the function with respect to w? That is itself a vector, okay? So if w has n components in the vector, the gradient with respect to w is also a vector with n components, and it is made up of the partial derivatives of the function with respect to each component of w. So you get the partial with respect to w1, partial with respect to w2, so on and so forth until you get the partial with respect to wn. So that would be kind of the first derivative, okay? First derivative. And so now, what would a second derivative look like? Or basically, if we want to do that, then we get the Hessian matrix, okay? And so if all of the, so I guess you have to assume that your partial derivatives are all kind of continuous, okay? Then you have the Hessian matrix, and this is going to be an n by n matrix, and so this will be basically the second order partial derivative of f with respect to w1, and then this would be, basically you take this derivative, partial of f with respect to w2, and then you take the derivative of that with respect to w1, and so on and so forth, okay? And then and you continue to do this, right? So you're going to get this thing. So if you look at each component, you can think of, let's say we take a look at this, the gradient, and we look at this first component of the gradient, which is the partial of f with respect to W1, we can think of, well, what if I took the gradient of this thing, okay? Well, I would get a vector of length n. And what would it be? It would be the partial of f with respect to 1 taken with another partial derivative with respect to W1 again, okay? And then I would take the partial of this thing with respect to W2, and I would get this. I would take the partial of this with respect to W3, and so on until I get the partial derivative of this thing with respect to Wn. So I would get basically all of the n terms here. I do the same thing with the second component in this gradient. The partial derivative of this thing with respect to W1 gives me this. The partial derivative of this with respect to W2 gives me this, so on and so forth until I get the partial derivative of this with respect to Wn, and so on and so forth. And that's how I end up getting an n by n square matrix. So you can think of taking, almost like taking the gradient of each component of the gradient, okay? And so if the gradient results in a vector of length n, then the Hessian is going to be a square matrix with dimensions n by n. All right, so when we look at a univariate function, the sign of the second derivative tells us about the concavity of the function. And there's something kind of similar ish, okay? So when you talk about, what's the sign of a matrix, it's a little bit different, right? We have kind of like the definiteness of a matrix, right? Is the matrix positive definite, negative definite, or something like that, okay? That can tell us about the curvature of the function as well, all right? So if the gradient of a function is equal to 0, so if the gradient is equal to 0, you're at some kind of local min, local max, someplace where the slope isn't changing. Basically, in every direction, it's flat, okay? Then you look at the Hessian matrix, and you look at the, basically your matrix of second derivatives, pretty much the Hessian matrix. And if it's positive definite, which is kind of the idea of a positive matrix, that is all of the eigenvalues of the matrix are positive, then the function is, quote, concave up at x, and x would be a local minimum. And if it's negative definite, then the function is concave down, x would be a local maximum, okay? And if it has both positive and negative values, then it's likely to be some kind of saddle point, and in that it's concave up in one direction, concave down in another. And if all of the eigenvalues are equal, or if it has eigenvalues equal to 0, then you would need more information. But this is kind of, it's not exactly the same, but for me, I find it helpful because matrix stuff and linear algebra stuff gets a little bit tricky. So it's easier for me to think of like unidimensional, one-dimensional things and relate things back to that as kind of an analog. So it's not perfect, this analogy, but I think it works fairly well. All right, there's links to some Wikipedia pages on the Hessian matrix. The Hessian matrix is usually symmetric, and there is a theorem. What is it called? What is this? That basically partial of the function with respect to W1 and W2 would be the same thing as the partial with respect to W2 with respect to W1, okay? You can also think of it as the Jacobian matrix of the gradient function, which is, good times, right? So all of our favorite things from 33a. Okay, but again, we can think of the Hessian matrix as a measure of curvature. So if you have basically a large second derivative, it means the slope changes rapidly, okay? And if we apply the Hessian matrix, okay, to the likelihood or the log likelihood function, we get an idea of the curvature of the function, and that in turn tells us about how confident we can be in our parameter estimates. All right, so this is a bit of a weird concept here, right? So I'm going to do it just for a univariate case, and then we'll try to generalize it to a multivariate case. I think it's a little bit easier if we start looking at just one variable and kind of get this concept of how confident are we in our parameter estimate, okay, based on one variable. So again, here is, imagine I have this bag and it's full of marbles. It's got some red marbles and blue marbles. You don't know what proportion is red, okay? You don't know what proportion in the bag is red. But we're going to say it's some fixed value, and what we're going to do is we're going to draw some marbles out, okay? So I draw 10 marbles with replacement out of the bag, and we end up getting 4 red marbles. So if we do this, and we say, what is the likelihood of getting kind of our sequence of data, whatever it was, we would have, so the unknown parameter of what proportion is red, well, we got 4 of those things, so we're going to do theta raised to the 4th power, and we got 6 values that were not, 6 marbles that were not red, and the probability of getting not red is 1 minus theta, and that happens 6 times, so we'd have 1 minus theta to the 6th, okay? And this would be kind of the likelihood of that, whatever exact sequence I had. If I wanted to say, well, the sequence doesn't matter, then I could multiply it by the binomial coefficient, but whatever, this is our likelihood. And so if I plot this and I say, well, let's plot this for all the values that theta could be. Theta could be any value from 0 to 1, right? The proportion that's red in the bag could be anything from 0 to 1. We know it's not 0 because I got a red marble, and we know it's not 1 because I also got marbles that were not red, okay? But it could be 1%. That would be surprising to us. It could be 99%. That would also be surprising to us because if it's 99% red, how did I get 6 blue? That seems very unlikely. And if it's 1% red, how did I get 4 red? That would be unlikely. So we're expecting probably something around 40% red, and values around 40% will be high. Could it be 50% red and I got 4 red and 6 blue? Sure, that seems pretty likely. And so what we're going to see is we're going to see the graph of the likelihood function, where we just say, well, you know, for different values of theta, what could it be? And this ends up being our picture. So 0, it can't be 0, because the fact that I observed some red marbles means it wasn't 0. Can't be 1, okay, because I observed some blue marbles. Values around 40% are high, and we would not, basically this says values like 40, 41, 39, these are very likely. This has high likelihoods, okay, that makes our data have a high likelihood. But values of around 50% still has a high likelihood, okay? If you told me that the bag is actually 50% red and 50% blue, I would believe that, because it doesn't seem that strange to get 4 red and 6 blue in there, okay? You could even tell me that it was 60% red, okay? And I would say, okay, a little bit surprising, but not that weird. If it was 60% red, could I still get 4 red and 6 blue? Sure, that doesn't seem that weird, okay? You know, on the other hand, if you tell me it's 80% red, I'd be like, wow, I really got a lot of blue. Okay, so that would be surprising to us. And if you told me it was only 10% red, that would also be surprising to us because I got 4 red marbles out here, right? So this is what we have. But so we have kind of this spread here for what we believe theta could be at this point. This explains what our likelihood function looks like. I've only given you one view quiz so far. All right, let me give you your second one, which is E. E as in elephant. E as in elephant is your second Euclid's answer. Okay, and so I think this slide just says what I just said out loud. 0.4 has the maximum likelihood. That intuitively makes sense. Values like 0.5 and 0.3 have high likelihoods, and that's what we have. Okay. What if I do the same thing, but this time I'm going to just draw a lot more marbles? Okay. So rather than 10 marbles, I'm going to draw 1,000 marbles with a replacement. And after 1,000 marbles, I got 400 red marbles, 600 blue marbles. Okay. So, and if I keep track and I say, what is the exact sequence? And I say, what's the likelihood of this exact sequence of data? Well, I have theta raised to the 400 power and 1 minus theta raised to the 600 power. What is this likelihood function? What does this likelihood function look like? Huh? It's a lot more narrow. So, I mean, first of all, the numbers, the numbers back here, 4 red and 10 out of 10 draws, the numbers are, they're not huge. 0.0012 is kind of our max. Now our numbers are going to be a lot smaller. Also, the likelihood function is a lot more narrow, okay? And so if we look at this, it looks like this, okay? In that, if I've drawn 1,000 marbles and 400 are red, now it is no longer believable that my bag is actually 50% red and 50% blue, right? So back here when I drew only 10 marbles and I got 4 red and 6 blue, if I told you the bag's actually 50% red, 50% blue, you would believe me, okay? You'd say, that seems reasonable, okay? Because you got 4 red, and we were expecting 5, and you got 4. That doesn't seem that weird, okay? On the other hand, if I drew 1,000 marbles, and 400 of them are red, and I said, I think the bag is actually 50, if I said the bag is 50% red, you'd say, you did something wrong, okay? Because if it's 50% red, you shouldn't have been able to draw 1,000 marbles and only get 400 red, okay? Because we would have expected 500 red, you only got 400. That is hard to believe, okay? But if I told you it was 41% red, that's acceptable. 39% red, also acceptable. Maybe even 42 or 38%. But basically, this is kind of the likelihood of for different values of theta. We also, if you look at the value of the likelihood, it's way smaller, on the order of 10 to the negative 293. So these are really tiny values. But basically, outside of this narrow window around 0.4, other values of theta are no longer believable. Okay. So this is what we have. So with more observations, okay, all right, so this, again, this is what we have. We have much less variance in what theta could be, okay? This is a lot more pointy in here, and we say, okay, values like 0.39 and 0.41 are acceptable, but we're not going to accept 0.3 or 0.5. Whereas back here, with only 10 observations, we would have accepted somebody claiming it to be 0.3, someone claiming that the theta is 0.5. We would have said, okay, I'm going to give you the benefit of the doubt there. Over here, not so much, okay? And so what could our theta be? There's a lot less variance here, okay? And so if we take a look at the second derivative of these functions, which basically measure the curvature, how rapidly does that slope change, we can see that the second derivative of the log likelihood function is much bigger, is much higher for the data when we have 1,000 draws. So for 10 draws, this was our likelihood function is theta to the 4, 1 minus theta to the 6. The log of that is 4 log theta and this. And the derivative is this, and the second derivative is this, okay? And if we take a look at this, what is the second derivative? Okay, we would get this and this. And basically, this versus this is 100 this is basically the same second derivative, okay? But it's multiplied by a factor of 100. Okay, it's multiplied by a factor of 100. All right, so what does this all mean? Okay, if I plug in, say, what is the second derivative at this point, 0.4, if I plug in 0.4 into this second derivative, I get 41.667. And over here, I would get 4,166.7, negative 4,160, okay? The second derivative measures the curvature of the function. And this tells us that has much more curvature. That is, it's much more pointy in that the slope changes rapidly, okay? We have a lot more curvature. And what this reveals to us, okay, is that we have a lot more information about where theta is located, okay? Again, we don't know the exact value of the proportion of red marbles in the bag. We don't know the exact value, okay? But after 1,000 observations, we have a lot more information regarding where it is, okay? Versus after only 10 observations, we don't have as much information. So basically, if I said, where do you think the value of theta is, with 1,000 observations, we have basically 100 times more information as we did when we just had 10 observations, okay? And that actually makes sense, right? So, so we have a lot more information about the location of theta. And so what we have is the relationship between the curvature of the likelihood function and the information we have about the parameter. This is kind of summed up with the Fisher information. Okay, so going back, I'm going to go back a few slides. This basically, the fact that this likelihood function has a lot more curvature, if that is, we measure the second derivative and we see that the slope changes rapidly here, this tells us that we have a lot more information about the location of theta than we did in this graph. Okay, and so the Fisher information is a way we can measure the information a random variable has. Okay, let me see if I can. All right, so it's a way for us to measure the information a random variable can provide about some unknown parameter, okay? Formally, it's the variance of the score, and that is, the score is the derivative or the gradient of the log likelihood function. You know, what's the variance of that function? And so, you know, let's say we have some kind of function that's the PDF, I guess PMF also, of some random variable x, given that we have some parameter theta, okay? And if the log likelihood is twice differentiable, the Fisher information is equal to the negative expected value of the second derivative of the log likelihood. Okay, so that's like a mouthful, but it's basically the pictures that we saw, okay? So if you think about the log likelihood of this PDF, okay, and you think about what the second derivative is, the second derivative would measure the curvature of that log likelihood function. And we're asking, okay, what is the expected value of that thing, right? So the expected value is taken with respect to this random variable, okay? So with respect to the random variable x here. So if I say, okay, what is the Fisher information? We might write it like this. We can also say the negative expected value, you know, with respect to this variable x of the second derivative of the log likelihood. So if we kind of plug this in, let's go back to that Bernoulli observation. Okay, so if we just say, how much information does one draw from the bag provide? Okay, so one draw has this PMF, okay? It's theta to the x, 1 minus theta to the 1 minus x. How much does one observation provide about the value theta? Okay, so we'll say, okay, well, what's the log of this probability function? Okay, so we get this becomes x log theta, and and this becomes 1 minus x log 1 minus theta. And we say, okay, what is the second derivative of this thing? Okay, well, the first derivative is going to be x over theta, and we got negative 1 over 1 minus x over 1 minus theta. And then what is the second derivative? Okay, the derivative of x over theta is going to be negative x over theta squared. What's the derivative of this with respect to theta? I get negative 1 minus x over 1 minus theta squared. Okay? And we say, well, okay, we want the expected value of the second derivative of the log likelihood function. Okay? It's the expected value with respect to the random variable x. Okay? Not with respect to the random variable theta. So we'll treat the thetas here as constants. Okay? So the expected value of x is over here. The expected value of 1 minus x is just that. And so this is our information that we have. Okay, and then so we'd say, okay, well, what is the expected value of x? Well, for a Bernoulli random variable, the expected value of x is theta. Expected value of 1 minus x would be 1 minus theta. And so this is what we have. I get 1 over theta plus 1 over 1 minus theta. And I can combine these things. And the information that one observation provides would be 1 over theta times 1 minus theta. And that would be kind of the Fisher information, or the second derivative, the expected value of the second derivative of the log likelihood function for this Bernoulli random variable. Is this okay? Okay, so there's a bunch of stuff here, and I think perhaps one thing that throws people off is that you're taking the second derivative with respect to your parameter theta, but then you're taking the expected value of the random variable x. Okay, those are different things. You got different variables involved here. Okay, Fisher information is additive. So if you have n observations, and I mean you could kind of derive this yourself as well, but if you have a whole bunch of observations, the total information that you have for n observations is going to be n over theta times 1 minus theta. And that aligns with what we had, right? When we had 10 observations versus 1,000 observations, those 1,000 observations was basically 100 times the information we had with 10 observations. Okay, so how much information do we have? Information is kind of it's an interesting thing in that basically, the data that you observe kind of provide information. It's not directly related to this, but our favorite YouTube channel, 3 Blue 1 Brown, has a video on Wordle, and basically a little bit of information theory there, and like how much information do you get when you get your guesses correct and wrong and things like that. And basically your correct guesses and your wrong guesses both provide information. When you have a wrong guess, you eliminate some letters and word choices, and that provides you information about the unknown values as well. Okay. So what is this? The previous example demonstrated that the second derivative of the likelihood function told us how confident we could be in our parameter estimates. All right, so let's take a look at this in the multivariate setting. And so the second derivative in a multivariate setting would be the Hessian matrix. And so let's take a look at this. So basically, we would now have a Fisher information matrix for a multivariate function, okay? And that tells us how much information we have about some unknown parameters theta. All right, and again, if the log likelihood function is twice differentiable, the Fisher information would be the negative expected value of the matrix of second derivatives, that is the Hessian of the log likelihood. So if you take the Hessian matrix of the log likelihood and you say, what is the negative of the expected value of x of this thing, that would be your Fisher information matrix. Okay, same idea, but now we're expanding this to kind of the multivariate case. So we can try this for linear regression, right? We're going to assume our outcome, the errors are normally distributed, and if that's the case, then we could say the probability function for each observation we have is the normal PDF with this mean and this variance, okay? And we're going to treat kind of our input values, x, as fixed values, all right? And sigma squared is fixed. And what we want to know is the Fisher information here. So we're going to take the expected value is taken with respect to the outcome variable t, whose distribution is defined by this function, right? So we want to know the negative expected value, okay, of this variable t, okay, with respect to this, and we're taking the second derivatives based on our unknown parameters, which are going to be w. So we have the log of this likelihood function. Okay, so if I expand all of this out, the log likelihood is this, and so now I want to get the derivative, or the gradient of the log likelihood with respect to w gives me this, okay, and this is going to be a vector of length k or whatever, however many values I have in w. Okay, so this would be the gradient, and then if I want the second derivative, or the second order gradient, okay, that is, I'm going to take this thing, and so this I kind of skipped over the steps to get to this point, and we're going to take, so this is a row vector, k by 1, and we want to take the gradient of this with respect to w, okay, or calculate the Hessian or the Jacobian of this vector, right? So we want to take get the Jacobian matrix of this vector, right? So that would be equivalent to the Hessian matrix. So we're going to take basically what is the partial with respect to w of this whole thing, okay? Well, there's no w here, so that gets eliminated. And what is this? Then we're going to get basically this square matrix of x transpose x. So I get 1 over sigma squared x transpose x, and this would be the equivalent. This would be the Hessian matrix of our second order derivatives. Okay, so this is the Hessian of the log likelihood, okay, matrix of the second order derivatives here. And we would say, okay, what is the negative expected value of this thing? Okay, what is the negative expected value, right? So with respect to our outcome variable t, okay, well, these things are all just constants here. So the expected value is just this, right? So the information that we have about our random variable t here is just this treated as a constant. 1 over sigma squared x transpose x. Okay, so what does this all mean? And I'm going over my time. Let me give you your last view quiz answer, okay? Last view quiz answer is B. B as in bear. B as in bear. So we're assuming this represents kind of the true relationship between x and t, and that our observations are just offset by some random noise, epsilon, okay? Sigma squared is the amount of variance we have in the noise. That is, if there is a lot of noise, okay, we have less information. And if we have less noise, sigma squared is small, we're going to have more information, okay? And we think about x over here, and I didn't include this, okay? If x spans a very wide range, you're going to have a pretty good estimate of your slope parameters as well. Okay, so if you just think of just simple linear regression, okay, if you have if x spans from say like a very wide range of values, okay, you can be a lot more confident in kind of your slope estimates versus if you only gather values from a small window. Okay, So if you're trying to estimate, what's the relationship between height and weight, it's helpful if you have some very short people and very tall people, okay? And you can get a pretty good estimate of your weight versus the relationship between height and weight. Versus if everybody you measure is, say, within a 2-inch window, okay, then your relationship between height and weight is probably going to be not very good either, okay? And I left that off a little bit, but that's kind of captured in this part with the X transpose X part here. Okay, let's end here. We'll call it a day. Have a good rest of your day. We'll see you on Friday.